Hi, this is my recording, or basically part one of my recording. Okay, chapter 12. Chapter 12 is our delve into creating models, estimate the impact of one variable on another. Okay, um, I think this is where it gets kind of interesting, and I think most um, work that you will likely do in a job entails a more complicated version of chapter 12, things in chapter 13, but we're not going to probably get to that in our class given the time constraint. Okay, simple linear regression model. Okay, a simple linear model. So first I'm going to introduce to you a deterministic model. What is a deterministic model? Let's assume there's some variable of y, the dependent. We usually call the dependent. And we're going to say suppose it's equal to alpha plus beta times x. Specifically, what this means is that x is linearly related to, y is linearly related to some independent variable x, okay? And the linear relationship has a y-intercept of alpha and a slope of b or beta, okay? This is classic equation. Okay? So here, this is the classic equation of a line, and this is what the model would look like if b was positive. We would say this blue line shows you the relationship between x and y, and when x is 0, y is alpha, and as x increases by 1 unit, y increases by beta. And that's just a, okay? All right, so this model, it basically is called a deterministic relationship because once you know x, you know exactly what y is. Okay, there's no risk of being wrong. You know exactly why. Okay, the variable interest is y, the independent variable is x. This linear equation determines an exact value of y when the value of x is given. Okay, so that's why it's called deterministic relationship. There's no way you'd be wrong what y is once you know it. The real world isn't so deterministic. Okay? The real world, where you model some variable y is some function of another variable x, there's other things involved that determines y, not just x. And because of that, you're going to be off by slightly a little bit. And this data set right here, we're going to use a lot in this lecture. This data set provides students, 10 students, and it gives their a math achievement score. So some score they took, like let's say the SAT version of math or something like that. And it gives them their final calculus grade, okay, as a freshman in college. And we're trying to see if you did well in this like math achievement score, like this SAT score in math, would you do better in calculus? Okay, so we have this data of 10 students. Okay, and let's just plot it. We're going to plot the grades. Okay, we're going to plot the math achievement score versus a calculus grade. Okay? Sorry. Let me scroll back up. Oh, there it is. Right. And you could see this point, it's more of a cloud. Yeah, this is an upward sloping cloud. Okay? Not exactly a round shape, but it doesn't all fall on an exact line. Okay. So we don't have this deterministic relationship. We move X, and we increase X, the math achievement score, yes, Y generally increases. But small movements at X, sometimes we see Y fall. For example, here, okay, we have X about 40 something, like high 40s, and the guy got or girl got almost 90% on their calculus test or grade or whatever, calculus grade. Someone else that did better on the math achievement score, like 52 or something like that, actually got a 75 or so, got lower on the freshman calculus grade. Okay? We should see it going up if it was deterministic. Okay? If we believe that doing better on the achievement test, we do better on this freshman math class, we should see it always going up. But here, it went down. And then again, go up a little bit more, it went up. Now you can see here, scoring 60 something, this guy should have did super well, but got an 83 or so, which is lower than this person here. Okay, so they don't exactly fall on a straight line. This is not a deterministic relationship. So now what we're going to do is we have to modify this deterministic relationship, okay, to model more what real life is like. And that's what's coming up here. We modify the deterministic model by adding a random error component term, EI. Okay, so this is all is deterministic plus this random part, EI. The error term explains the deviation of the points from some determined line. In our case up here, we believe there's a positive relationship between the score and the grades, but there's some deviations. Whatever we think that positive linear relationship is, say a line, okay? So let's draw this. Okay, maybe it's something like this. Okay. You could see, other than maybe this point, all the points are off the line. Okay. And then being quote unquote off this line that we think is the relationship between scores and grade, that's captured by the error term. Okay, that's captured by this. Okay. Oh, let me erase the line. All right. So we're going to say there's a model here where yi, for the ith person or the ith data point, is equal to alpha, the y-intercept, plus beta times xi, the independent variable, plus ei. Error. Okay. Alpha and beta are the population parameters, or the coefficients of the model, and ei is the error term. Okay. And this is the random variable. Okay. The deterministic part, alpha plus beta x, we call that the line of means. This is the line component. Okay. And the epsilon, the fancy E, that's the error term. That's the error component. This term is to show that the actual individual response Y deviates from the line of means. Okay. All right, let's move on. All right, so now what we're going to do is figure out how we're going to build up to how we estimate this model. Okay. Meaning estimate the parameters alpha and beta. All right. Our regression, our simple regression analysis, one reason why we call it simple is we only have one independent variable and one dependent variable. No, we're ignoring everything else that exists in the world that can affect your scores. Okay. So, yeah, we have this relationship here between math achievement score and final calculus score. And yes, the better you do on the math achievement score, the better you'll do on the final calculus score. But it is quite possible that someone did really well on this math achievement score when they were going to take the calculus score. Maybe they're on a fight with their boyfriend or their girlfriend. They were just not in the mood to take the, maybe their dog accidentally passed away or something. They're just not in the mood to take the test. And they just did bad poorly on the test because of this random negative shock of fighting with your girlfriend or boyfriend or something. Okay. Or maybe they partied the night before and they got super drunk. All of these things will impact the calculus score, but it is not in this model. All this model shows is a relationship between math achievement score and the final calculus grade. Okay? And this is off from the line of means because all these things that I discussed and more. Okay. We only have one independent variable and one dependent variable. No, we are ignoring all other things that may affect y, even those that affect both x and y. Okay. So we can potentially have something called an omitted variable bias. Okay. What is the omitted variable bias? Omitted variable bias, the classic example that I've been giving in this class, is cancer, smoking, and lighters. Okay. If you omit something, okay, let me draw this out. Suppose we had something like cancer, something like cancer that goes up. Oh, sorry, wrong one. Suppose we have something like smoking, and someone who smokes more, that's going to cause them to buy more lighters, but it also causes the chance of getting cancer to go up. Okay. So smoking causes both lighter purchases or ownership to go up and probability of cancer going up. Suppose some analysts did not collect data on this. They didn't collect data on smoking, and they only collected data on lighters and cancer. Then what they're going to see is that as lighter purchases increase, cancer purchases increase. Specifically, they're going to see a positive relationship between owning lighters and getting cancer. Well, someone could falsely conclude then that, well, if you get rid of all the lighters in your house, you're not going to get cancer. That's a classic example of an omitted variable bias or omitted variable error or whatever you want to call it. The variable omitted in this conclusion or the analysis that we just did is smoking intensity. The more you smoke, the more lighters you buy, and the more chance of you getting cancer, right? That is excluded from the analysis. All we observe is lighters and cancer. So we think increasing lighters increases the probability of getting cancer, which is clearly nonsensical. Okay? So we need to be careful of these kind of concerns and issues that we may run into when we have a very simple model with only one independent variable and one. Okay, let's move on. Uh, Now, the relation the book covers, and this is chapter 13, unfortunately, regression analysis involving two or more independent variables, and this is called multivariate regression, multiple regression, or something like that. Unfortunately, I don't think we'll do that, but if we do, that's in chapter. Okay. Now, assumptions on the random variable, the epsilon I, or fancy EI term. Okay, the in random error. This error term is going to be assumed to be independent random variable in the probabilistic sense. Okay, meaning the 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 error term EI for the ith observation being 1 through n, they're all going to be independent of each other. Okay, the mean, on average, we're going to expect epsilon I to be 0. Okay, with the mean of 0 and a common variance equal to sigma squared. So all of them have the same variance of sigma squared. So on average, we expect no one to have an error, or expect an error to be 0. Meaning, on average, we're going to expect this to disappear and y equal to the line of means. Lastly, we're going to assume the distribution of the error term is normal. Okay, or the error is normally distributed with the mean 0 and a variance of sigma squared. Okay, so this is what it would look like. This is a line of means, and we're going to assume for any given x, the highest chance you have is being on the line. But it is quite possible that because of this error term while we expect it to be 0, could be different from 0. It could be above the line or below the line. Okay? Same for this x and same for this x. All right, let's move on. All right, so let's keep going. This part says basically the expectation of y is just a line of means, alpha plus beta xi. Remember, the expectation of the error term is 0, so that's why it's not here. And this estimate is considered the best fitted line, and the best fitted line is called the least square line or the regression. Okay, just different terms. All right, the method of least square. How do we estimate alpha and beta? We estimate alpha and beta using the sample of data we collect. We collect a sample of data. We believe there's a population parameter, alpha and beta. We don't know it. We don't have enough information to get those alphas and betas exactly because we can't collect data on everybody in the population. So we get a sample and we estimate alpha, and the estimate of alpha is A, and estimate beta, and the estimate of beta is B using the sample. Okay? So if we use A and B, A plus B times some X, we get Y hat. Okay? And Y hat is the estimated Y given we have A, B, X, I, okay? And some X. All right, let's move on. We have the data again. And they say here, look, this is the best fitted line. So how did they get this? How did they get alpha of 40.78 and not alpha, A of 40.78 using this data and B of 0.766? Let's go through it, okay? And basically, when you have a data and you calculate A and B, A plus BX is equal to Y. You could draw this line. This line is basically showing this relationship. There's a y-intercept of 40.78 right here, and the slope is 0.766. Okay? And this line fits in between all of these points. Okay, that's the quote-unquote fitted line given the data. All right. So what is this data? Okay, the vertical line drawn. So let's analyze this vertical line drawn. From the predicted line to a particular point represents the deviation of that point from the line. Okay, so look at this. Here is the line. This line is given by this line's equation is this. If you put in some x here, and here that is, looks like it's about 90, 89, and a little less than 50. It looks like we put in this, we have observation 6, student 6. You put in 47 for x, you get 89 for y, okay? So you put in 47, and you get 89 for y, okay? But we didn't get 89. We get a different value using our line, okay? Let me show you that. Let me go change the sharing parameters. Okay, I'm opening up Excel. And let me share differently. Okay, hopefully you could see Excel and Word. And so the first thing I'm going to do is copy the data in. Okay. Here. And okay, what did I do? Okay. And we have this line, okay? So we're going to say grade and is equal to 40.78 plus 0.66. No. 0.766 times score. Okay. So let me see, it's grade. And this is equal to 40.78 plus 0.766 times. And I'm going to link it to this cell here. And I'm going to call that score. Okay. And I'll highlight it in yellow to say I got to put a number in there. Okay. Okay. So let's try to see if we could replicate this analysis right here. If I put in, say, 47, the grade that we calculate is 76.78, which put in 47, that's about right here. Yeah. So what the line is doing is trying to give us the best estimate of what the grade would be if we give the final calculus grade would be given this. Okay, and it's right here. But clearly this person got 89, which is above that. So difference between 89 and what the model calculates, which is 76.78, that is basically the error. Okay, so let's calculate that. And that is yi minus y hat I. Okay, well, and this is equal to the yi, which is the actual grade 89 minus the estimate, and we're off by 12.22. Okay, and that's the error term. That's the error term. That's the error in our model. Okay? All right. So the process finding alpha A and B is what we're going to do is try to figure out how to find A and B to create the quote the best model. And what is the best model? The best model is a model that minimizes this error. Okay. And of course, it's not just for one, but for all of them. It minimizes the error in the analysis. Okay. So that's the principles of least square. All right. So this is the procedure to use to find A and B. And it's SSE, or sum of square errors, or sum of square residuals. Residuals is another word, fancy word for error. And it is to minimize this formula, which is by picking A and B. And it's a sum for each observation, yi, the actual y, minus yi hat, the estimate using the model squared. And why do we have to square it? It's like the variance. We didn't square it, the positives will cancel the negative. Okay. To avoid the positives and the negative distances from canceling each other out, right? This positive and this negative canceling each other out, we choose to minimize the distance, okay, using the square, the principles of least square. Okay. So here we go to this by substituting A and bxi in for yi hat. Okay. And again, this whole thing, we call that error. That's just the error. Yi minus a minus bxi is equal to the error term. And here, because it's not epsilon because that's the quote unquote true error, it's e because that's the estimated. Okay. And I put a hat on there. Maybe I shouldn't. All right. So how do we minimize that? Okay. And it's right here. This is the derivation. And because we don't use calculus in this class, you don't have to know step by step. So I'm going to kind of skip through this. Okay. But you take a derivative of the sum of square error with respect to A, and you set it equal to 0, and you go through this, all this hocus pocus gobbledygook, and you find A is equal to the average Y minus B times average X. Okay, so you cannot find A without finding B first. So, okay, let's try to find B. Well, what do? You again take the derivative, the partial derivative of SSE with respect to B. And again, you go through this, all this abracadabra stuff. Okay, and you go more abracadabras. And then you get B is equal to SXY divided by SXX, whatever that means. And that is the sum of xi minus x bar times yi minus y bar divided by xi minus x bar squared, where x bar is the mean for the independent variable, y bar is the mean for the dependent variable. So what you have to do is you got to first find B, and given that you know B, you plug it in here to get A. So what you have to do is know how to do just the bolded part, what A is and what B is, okay? So what we will do is let's find this. Let's find A and B using this data, okay? And we're gonna do it the quote unquote long way using this math, okay? First, we're gonna have to find B as this gobbledygook, and then we're gonna find A, okay? So let's do this, okay? All right, so we have this, and what I'm going to do is label this thingamabob, okay? So we know what this is. The math achievement scores, okay, these are the XIs, and the final grades, these are the YIs, okay? So let me, Roman, Okay. Okay. We'll do. All right. So I'm going to squeeze this a little and open this up just for now. And let's not look at the answers and let's look at this stuff, okay? Because I might not follow. Well, maybe I should, huh? Eh, okay. Well, I'm gonna just follow this B and A formula. All right. So let's look at this. To find a B, I need to find the average X and the average Y first. So let's do that, okay? Okay, so we'll do X bar, Y bar. That's the first thing we gotta do. So X bar is equal to average of X's. Y bar equals to average of Y's. Okay. All right, so we did that. What's the next step? We got to find X bar, Y bar, and then we got to find the difference between Xi and X bar. So let's do that. Okay, Xi minus X bar, and we got to find the difference between Yi and Y bar. So let's do that. Okay. This is equal to Xi minus X bar, and I'm going to press F4 to put dollar signs on X bar because I'm going to copy and paste the formula all the way down. And you could see while the Xi's changed, the X bar does not. And that's what we want. We got to do the same thing for Y. Yi minus Y bar. And again, put the dollar signs on the Y bar. Okay. Copy the formula down. Check. Yep. Y bars are changing. But I mean, Y's are changing, but not the Y bar. Okay. So we did that. And then now we're going to do Xi minus X bar squared. Okay. So this is Xi minus X bar squared. And that's just squaring of these guys. So I don't have to recalculate to square those. Okay. It's this squared, caret 2. And we're going to scroll that down. Yep. Okay, so we did that. All right, so now what do? We gotta multiply these two together, sum them up, and divide it by the sum of these guys. All right, so let's do that. So this is Xi minus X bar times Yi minus Y bar. Okay. And this is just this guy times this guy. Okay. So I have to add them up. So let's do the here. No, let's just do it here. Sum and equal to sum. You add all these guys up. And sum, and we have to add, yeah, we have to add all of these guys up. Okay. Those are our sums. So then our beta, or B, I'm sorry, B, is this dude divided by this dude. So it's B, and it's equal to this dude divided by this dude. And we got this. Okay. All right. Hey, it looks like that number. Looks like we got similar numbers. Okay. Obviously, our number is more exact because it's not rounded. All right. Now we got to find A. So let's scroll up. A is equal to average Y minus B times average X. We got average Y, average X. So A is equal to average Y minus average X times B. There it is. We just did, we just found the two coefficients, okay? Y-intercept and the slope. And that's how you build a model. So let me scroll down this way, this way. Okay. And that's how we did that. All right. There's another example here with Armand's Pizza Parlor. You guys could do that yourself, but it's the same thing. Go through the steps and you could figure it out. All right. Okay. But do you have to do this all the time? No, we could use Excel. Okay. And as the analysis data path showed, we could use Excel to calculate regressions. So let's do that now. Okay. Let's go out. So how do we do that? Well, I'm going to put the cursor somewhere, like right here. You don't have to, but go to data, data analysis. You look here and you look for regressions. There it is, regression. Press OK. Input range. Okay. Here, you got to put in the Y's. Here's the Y's. Okay. Notice I did not include the header. Now, the header right now is kind of messed up. So let me get out of this and do it correctly. Okay. The header's in three different, like, I'm gonna merge them. I'm gonna put them all into one cell. Okay. So let me try that. It was just a problem with the way I there, and I'll call this math achievement score. Okay. And we'll call this final calculus grade. And I'm going to delete these two columns. Should have done this before, but I forgot. And because I'm anal, I got it there. And let's make sure this is all there. Okay. So, yep, they're all in single cell. Sorry about that. Why do I care? It allows us to label better using the data analysis tool, regression. Okay. Y range. Now I click on everything, including the label. X range, click on everything, including the label. And if you include the label, you got to tell Excel you did, or it's just going to blow up on you. It's going to screw up on you. Constant is 0. No, we want them to estimate the y-intercept. Don't click on that. Okay. And for now, everything else here, we haven't learned about, so we're not going to do it. Confidence level. I'm not going to do any of that. And let's press OK. Okay. Oh, you know what? Let me get out of this. I want to do it differently. Okay, sorry about that. I'm an idiot. Let's try that again. Regression, okay, everything's there. I don't want to put it in a new worksheet. I want to put it in an output range. And output range allows me to put it in the same tab so I could add the data. So I put it in this tab. And what it's going to do is ask you, where do you want to put it? And you got to pick the left uppermost cell. So then if you click on this cell, it's going to put the information this way. Okay. So just click on one cell like that and then press OK. And you could see it started from this cell that I clicked on, and all the information is to the right and bottom of that. right? So then let's format it a little, okay? Like this, okay? And I know this is a kind of strange bit of information, okay? Um, and I'm gonna just format this. Format all these gobbledygook of numbers. You know what? Let's turn it to zeros. Do something like that. Format all of these numbers like this. And that I'm formatting so I could show it with what we have. All right, so let me delete. Let me shrink it. All right. Well, what's relevant is the coefficients. Okay, I know we haven't learned what all of this weird gobbledygook of numbers are here in the output. Okay, and that's basically the goal of chapter 12 is I'm going to show you what all of this stuff is. Okay. One thing we know is this is the summary of output. We know the number of observations. Right here, 10. We have 10 observations. All of this stuff, standard error, adjusted R squared. I know you guys heard of these things, R squared, you know, but we haven't learned it yet. And what's important is here, the coefficients. These quote unquote coefficients gives us the estimate of A and B. Okay? You could see the intercept, that's just A, and you can see 40.7842, 40.7842. And the math achievement score, this is B, 0.766, 0.7, well, that's just B. Okay. These are the standard errors. Yes, we haven't gone into all this, but so far what we learned is this, okay? And our goal is to learn all of this in chapter 12. Okay, all of this right here. All right. Um, let's go there. And we are going to end our lecture of part 1 of chapter 12 at this point and start part 2 at section 2. Have a good day.